Definition 6.41 Congruence L for trees. Let X not in sigma be a new symbol. For labeled trees T1, T2, we will say that T1 congruence L T2 if and only if for all trees T in sigma the set X star star which have exactly one leaf labeled X and all other nodes in sigma star star we have T1 dot X T in L if and only if T2 dot X T in L. That is for all tree T if we concatenate the root of T1 to the leaf of T labeled X. The result is in L if and only if the same holds for T2. The analog with the classical right congruence L is obvious. In a similar fashion, we may define an equivalence relation to be a right congruence over sigma star star if and only if for all T1, T2 in sigma star star, T1 Myhill Nerode congruence T2 if and only if for all T in sigma of the singleton X star star with exactly one leaf labeled X, T1 dot X T, Myhill Nerode congruence to T2 dot X T. Theorem 6.42 The Myhill Nerode theorem for tree automata. The following are equivalent. 1. L is finite state over sigma star star. 2. L is a union of equivalence classes of some right congruence R of finite index over sigma star star. 3. Right congruence L has finite index over sigma star star. Proof. From 1 to 2 and from 2 to 3 are virtually identical to the arguments for standard languages. For instance, consider 1 to 2. Let M be a finite state accepting L. As with Theorem 6.21, we declare that two trees T1 and T2 are equivalent if and only if M takes them to the same state, i.e. from Q0 on all the leaves. Then R is a right congruence and has finite index as M has a finite number of states. Hence 1 implies 2. We need a little work for 3 implies 1 since delta is now more complex. Suppose that L is the union of equivalence classes of right congruence L which has finite index. Again, we can let the states of the machine M we construct be the congruence classes of the right congruence L. First, we observe that for any tree T1 right congruence L to T2 and A in sigma for D which is less than F, the fan-in bound of sigma star star, which is F, and the trees Q1, Q2, and so on until QD in sigma star star, we have T1 dot A Q1 dot A Q2 and so on dot A QD, which is right congruence L to T2 dot A Q1 dot A Q2 and so on dot A QD. This follows from the fact that T1 dot AB equals to T1 dot X dot AB for any B in sigma star star, replacing the QI one at a time. The observation generalizes to establish the following fact. For any trees T1, T2, T3 until Tm, and T1 prime, T2 prime, and so on until Tm prime, with M which is less than or equals to F, if for all I, Ti is right congruence L to Ti prime, then for all A in sigma, T1 dot A, T2 dot A, T3, and so on dot A Tm is right congruence L to T1 prime dot A, T2 prime dot A, and so on dot A Tm prime. Now define delta of the set T1, the set T2, the set T3, and so on until the set Tm plus additional item A equals to the set of T1.A, T2.A, T3, and so on .A, Tm. From the fact above, it follows that if we specify delta in this way, then delta is well defined. The accepted states are again the set of set T such that T is in L, and again as in Theorem 6.21, the initial state is the set lambda. Notice that again we will get an implicit minimization algorithm from the Myhill-Nerode theorem for trees and a method of test sets.